Hello students, today's video is on types of electromagnetic waves. This video is due on semester 2, unit 1, day 5. So we're talking about a new type of wave, electromagnetic waves. You'll learn more about what electromagnetism actually is later on, but right now we're just talking about the waves, which travel without a medium. Remember, a medium is a physical substance, so these waves do not use a physical substance. Instead, they travel with what are called photons. The definition of a photon is a particle of light that carries energy. Photons have absolutely no mass because they're not made of anything. It's not like they're a gas, it's not like they're a solid or a liquid. Literally, they have nothing, okay? They're just energy. And because they have no mass, they can travel through a vacuum. So, for example, they can travel through space. The definition of a vacuum is an empty space that has nothing in it. That is why, for example, light, which is a photon, can travel from the sun to Earth. It can travel through this empty space between, here's the sun, here's Earth. It can travel from here to here, unlike sound. Sound can't travel unless there's a medium. So light works in space, but, sorry, that's a check mark, sound does not. The speed of light is this big number. Usually we just say 3 times 10 to the 8th meters per second. So we kind of round. So 3 times 10 to the 8th, if you remember scientific notation, is 300 million meters per second. Light or photons can travel through mediums. They don't need mediums, but they can go through them. If they do, though, they go slower. So photons travel slower in glass than they would in outer space. This is the electromagnetic spectrum right here that you're looking at. Electromagnetic waves are commonly called light waves. It's a little misleading, though, because not all electromagnetic waves can be seen. The only ones that can be seen are the visible ones. So you can see here, it tells you how big they are. So radio waves are about the size of buildings. Microwaves are about the size of butterflies. Infrared, about the size of a needle point. Visible is about the size of bacteria. Small organisms. Ultraviolet is about the size of a small molecule. X-ray is an atom, and gamma ray is like the inside of an atom. So you can just see that they are getting smaller and smaller. The wavelength, which is, remember, the size of the wave. Remember that wavelength and frequency have an inverse relationship. So as wavelength increases, frequency decreases, or vice versa. So you can see here, this is a long wavelength, but because this is a long wavelength, that means there's very few vibrations, which means this is a small frequency. So you can see here, wavelength is getting smaller, and frequency is getting bigger, because frequency is the number of vibrations. So we can see we've got a lot of vibrations here, but they're small waves. So small waves, big frequency. Big waves, small frequency. Hopefully most of these look familiar to you. Radio waves, obviously we use in radios. Microwaves and microwaves. Infrared, if you think about infrared goggles. Visible light is all of the colors. You can see right here we've got all the colors, Roy G. Biv. Ultraviolet light, like this is from the sun, for example, UVA, UVB rays. X-rays, obviously you get those at the doctor's office. Gamma rays, these come from nuclear radiation and are very dangerous for us. The most important part that we're going to be focusing on this unit is the visible light part of the spectrum. So how big the wavelength of the visible light spectrum, you can see it goes from 760 nanometers being the longest, which is red, all the way down to 380 nanometers, which is the shortest, which is violet light. Now, nanometer, right here we can write nanometer. Nano means super, super tiny. So if you think about it, 80,000 nanometers is about the size of the width of a human hair. Not the length of it, but literally, like, if you were to look at the end of your hair, that's how big the end of your hair would be. So these right here, oops, sorry, I think I had to erase those. These right here are super, super small. Remember that white light actually contains all colors of light, so if you were to shine white light through a prism, you would be able to separate out all of the lights, all the colors. And remember, they go in order of R, O, Y, G, B. Technically, there's indigo in here, and V, Roy G. Biv. So red, you can see this table right here. Make sure you get this down. You want to know the approximate wavelengths that these colors coordinate to. Just remember, red is the longest, violet is the shortest. Now, this is a picture of your eye. This is the pupil right here. This is the big circular squishy part of your eye. And behind your eye, right here, you can see we're kind of zooming in. There's all this weird stuff that's really important for you to be able to see. And what I want you to focus on right here is that you can see these little colorful cones. So this is a red cone, this is a green cone, and this is a blue cone. So keep that in mind for the next slide. So those cones in your eyes are sensitive to 3 colors of light. They're the same colors as what they were colored on the previous one: blue, green, and red. So that is what your eye sees in. So you can see here's our spectrum again, from 400 nanometers to 700. And your eye is sensitive to seeing blue at the lower end, green at the average, and red at the higher end. There's also a little bit of red down here that your eye is sensitive to seeing. Those cones are sensitive to seeing. But generally, we call this cone the red because it overlaps most of the red, even though technically that cone can see a little bit of the blue as well. Which therefore means that the primary colors of light are in reality, keep in mind this is of light, based on what your eyes can see. So the primary colors of light for your eye are red, which is pretty obvious, blue, which is pretty obvious, and green. Okay, those are actually the primary colors of light. Keep in mind I'm talking about light, not pigment. Okay, so if we take 3 flashlights, we've got a red one, a blue one, and a green one, and we overlap them, we can also find the other wavelengths. Sorry, the other wave colors. So these secondary colors of light, red and green, if you put 2 red and green lights together, you end up with this yellow right here. Here we go. If you put green and blue together, you end up with this cyan color right here. And if you were to put red and blue together, you end up with what is called magenta. Sorry, I don't know if I really have a magenta color. Here we go, magenta, which is kind of a purplish pink. And you can see that right here. If you put all of those colors together, you end up with white in the middle. Now, the reality is that in color, the colors that you see of something are actually only the reflected color. So, a red shirt is going to absorb the other colors in the previous wheel, which hopefully you drew down. So a red shirt is going to absorb the blue and the green, and is going to therefore reflect red. A blue shirt is going to absorb the red and the green and reflect blue. And a green shirt is going to absorb blue, and red and reflect green. So you can see here, the reason a red shirt is red is because it's reflecting red light. The reason a blue shirt is blue is because it is reflecting blue light. These right here are the primary colors of light, not of pigment, of light. Okay, a magenta shirt, on the other hand, these are our secondary colors. So a magenta shirt is going to go ahead and absorb, it absorbs green color, and therefore it reflects blue and red, which your eye interprets as magenta, because blue and red together will make the secondary color magenta. A cyan shirt is going to absorb red and will reflect that blue and the green. okay, which together result in your eyes interpreting that as cyan. And then a yellow shirt is going to absorb blue and reflect green and red, which we learned green and red light put together will create yellow. And so these are the secondary colors of light. Remember, what you see is based off of the reflection. A black shirt is going to absorb all of these colors, so it'll absorb blue, green, red, and will reflect no color. Okay, so we end up not seeing colors, so that's black. And a white shirt will absorb no colors and reflect all of the colors, which we've learned that all of the colors put together end up equaling white. Alright, that's the end, what you should have in your notes. Our new vocab: electromagnetic waves, photons, vacuum, visible light, tones, the primary colors of light, and the secondary colors of light. We'll actually talk about tertiary colors of light, and then we'll talk about pigments in class. You should also have the diagrams for the electromagnetic wave spectrum, the visible light wavelength and frequency chart, and we'll talk about the color light wheel more in class. Although you should have the those overlapping ones that I showed you drawn in your notes on page 9. Alright, see you guys later.